And just starting again with sort of some general information about the electromagnetic radiation unit, and then some common mistakes. Remember that you need to have basically the electromagnetic spectrum memorized. You have to be able to classify major portions of the spectrum by wavelength, frequency, and energy. So you want to just pick one, and I think it's probably easiest to memorize wavelength, because then you can determine frequency by using V equals lambda times F. And then remember, energy is related to frequency. So energy is directly related to frequency. The higher the frequency, the higher the energy. You also need to be able to compare natural and technological processes by which electromagnetic waves are produced. So there's a column in the chart in your textbook that has how it's created, how that EMR is created. I'll just give you the page numbers here in case you forgot. This is on page 676, the list of all the wavelengths of the different colors, and then the main chart of electromagnetic radiation is on page 638. So students often have difficulty calculating the number of photons emitted by a source given the total energy of the rate of emission. So remember, on your formula sheet, E is equal to H times F, which is HC over lambda. But what you really want to get into the habit of doing is putting that N in front of it, so that you can solve for the number of photons. So that's what it says here, that number of photons is that N. There will be no ray diagram questions at all. Ray diagrams are only used as a tool to determine characteristics. So you do not have to do ray diagrams. You do have to be able to determine the characteristics of an image using the formulas. You can still use ray diagrams, you're just not expected to. They're not actually part of the curriculum. And then often the wrong formula for diffraction is used. So remember, there's two. There's lambda equals d sine theta over n, and lambda equals xd over nl. And you always have to check your angle. And then this formula is only good for theta less than or equal to 10 degrees. Otherwise, use this one. I'd say use that one always, unless you specifically have to use this one to solve for something that isn't in here, like L or X. So then part of the theory that you have to do, and this is sort of part of it, is that trace the evolution of the model of light. So we talked briefly about the initial particle model of light, which was what was put forth by Newton, and it was believed for hundreds of years that that was true. And then we looked at the wave model of light, and two things that really ended up supporting the wave model of light are Huygens. Oh, I'm not even spelling that right. Let's try. Huygen. So Huygens principle, and then Young's double slit experiment. Then there's the quantum model of light, which is really supported by Planck and Einstein. And so that relates to the photoelectric effect. And wave-particle duality, and that's just that photons of light have both a wave nature and a particle nature. And the wave nature usually comes about when they're traveling. So how they travel like a wave, but they interact with matter as a particle. Board. Again, I've got the electromagnetic radiation, the electromagnetic spectrum. So there's a part from memorizing the info. So memorize the constituents. And then within that, as well as Maxwell's theory of EMR. So you should know the 6 parts of that are in your notes. Included in that, part of that is the universal wave equation that just says the velocity of a wave is equal to the wavelength times the frequency. And this is for waves, this one. And when you're talking about specifically about EMR, you use C is equal to lambda times F. So about measuring the speed of EMR, you need to know a little bit about the history. So just have an awareness that there is a history there. And the people we talked about were Galileo. We talked about Romer, Huygens, the same person, the same Huygens of the Huygens principle, and Fizeau and Foucault. So just have, I don't think I spelled that right, F-O-U, oh yeah, that was right. And then the main one to know about is Michelson, with an N-sided mirror. Right, and the formulas that you need to use for that are on your formula sheet. The formula for period is 1 over frequency, and velocity is distance over time. But what you do is to find V, you find the period if you know the frequency. So period is 1 over F, then time is period divided by the number of sides on the mirror, and then velocity is 2 times the distance over time. Remember, you have to multiply that distance by 2, the distance being the distance between the mirrors. If you want to go backwards, you would just go this way to find either F, D, or T. So on the next page, then we looked at different properties. We covered a whole bunch of different properties of EMR. We looked specifically at light, but anything we found was true about light, we could extrapolate that it was also true about EMR. So the first was a law of reflection that says the angle of incidence is equal to the angle of reflection. And having a flat mirror, we want to remember that you have to draw on a normal line. So this is the normal line, and that's 90 degrees. So that's supposed to be an N, whatever it looks like there. And then you have the angle of incidence, is always measured to the normal line, right? It's always measured to the normal line, not to the mirror. That's the thing you need to remember. And then that's equal to the angle of reflection. Okay, so that's a rule there that needs to be memorized. So it's not on your formula sheet. Okay, so curved mirrors and thin lenses. So the characteristics, these are the characteristics that, of the image, or characteristics that you need to know if you're given information about an object and you want to figure out about its image. So magnification can be same size, it can be enlarged, it can be diminished, or smaller, larger, smaller. The image type can be a virtual image. If it's a rect, it's virtual. If it's a rect, DI is negative. If it's a virtual image, then the image distance must be negative, because it means it's on the wrong side of the mirror, the wrong side of the lens compared to where it should be. So in terms of a mirror, it means it's behind the mirror. In terms of a lens, it's on the same side of the lens as the object. And usually the image is on the opposite side of the lens. If you remember the lab that we did, the image was on the piece of paper. Like you had the object here, the lens in the middle on the piece of paper, and the image showed up on the piece of paper, and that was real. Virtual are always on the same side as the image, or of the object with lenses, and on the opposite side of the object with mirrors. A real image, they're inverted, so your HI and your magnitude, so your image height and your magnitude are negative. And for a real image, all the rays are real. For a virtual image, at least one ray is virtual. Then there's the image attitude, which is erect or upright, which means it is virtual. Okay, and it's either behind the mirror or in front of the lens. I should put in here. Okay, and then this is behind lens. And the thing you want to remember is that virtual and erect go together, and real and inverted go together. It can't be any difference. If you know it's virtual, it has to be erect. If you know it's real, it has to be inverted. Those two should never be confused, right? This always means erect and inverted. Then looking specifically at quantities, you have to make positive or negative, like your sign conventions for mirrors or for lenses. Mirrors can either be converging or diverging. This should actually be indented a bit so it lines up with converging, just to make it nice and neat, but I forgot that. So converging mirror is a concave mirror. The focal length is positive because it's a real focal point. And it has real or virtual images, and if it makes a virtual image, it will be bigger than the object. So anytime you have a mirror that produces a virtual image that is larger than the object, you're dealing with a concave mirror. Diverging or convex mirror, the focal length is negative. All images are virtual, upright, and smaller every single time. Okay, can't ever be larger. And then it's similar for thin lenses. Converging lens or convex lens, the focal length is positive. It's a real focal point. Real or virtual images, again, the virtual images would be bigger than the object. And diverging or concave lens, the focal length is negative. It's a virtual focal point, and all your images are virtual, upright, and smaller. And I just want to double check because the terminology that they use between mirrors and lenses is different. I'm pretty sure for mirrors they use concave and convex, and for lenses they use converging and diverging. I just want to double check that I have that right. Okay, yeah. Mirrors are, for mirrors, they use the word concave and convex. For lenses, it's converging and diverging. A converging lens is a convex lens. That's easy to remember because the first four letters are the same, and then it's opposite from mirrors. A converging mirror is a concave mirror. A diverging mirror is a convex mirror. Okay, so then there's the two equations used for mirrors and lenses, curved mirrors and lenses, the magnification equation and the thin lens or the mirror equation. These are both on your formula sheet. Refraction, the big one is Snell's law. So this one is on your formula sheet. This is just, you don't even need to worry about this. This is just a special case of Snell's law when you're going from air into something else. So this is from air into medium X. And it can be written this way because the index of refraction of air is just 1, right? And so then this is taking, like, this is just a special case of N2 over N1 equals V1 over V2, where N1, 1 is air, so N1 is 1, and V1 is just C. But it all comes from this. Same thing with the critical angle. The total internal reflection, or the formula for the critical angle, what this means is that at the critical angle, okay, all light refracts at 90 degrees. So what that means is theta 1 equals theta C, and theta 2 equals 90 degrees. And then again, this becomes a special case of this, just using this information here. Okay, so then we're going to move on to diffraction. Huygens principle. Remember, it's just that each wave is a number of tiny wave point sources called wavelets. So you start with whatever your point source is, and it goes out in a wave like this. And then all Huygens is saying is that that particular wave has a whole bunch of little point sources on its own that then each cause a new wave front to move from. And then that's how it is that waves end up kind of going out in concentric circles from an original point source. I'm not going to draw too many on there. It's sort of a minor little thing, and I can't actually imagine you getting asked a very specific question about it. It would be as part of the model of light. And then I already mentioned the two different formulas for diffraction. This is the small angle approximation. Sorry, is this one, lambda equals xd over nl. And you have to make sure that you check that angle. where this will be L and this will be X, and theta needs to be less than or equal to 10 degrees. If it's over, then you use this formula. This one's always safe to use. And then remember how to find, if you're given, a number of lines, say per millimeter, to change that into D, D has got to be 0.001 over the number of lines. So really this is equal to the inverse of D. But you need to write, but the distance, distance must be in meters. And then also just know what polarization is. And how to tell if something is polarized. Okay, and that brings us to Planck and the photoelectric effect. So Planck's formula E equals NHF over lambda. So remember what's on the formula sheet is E equals HF, which equals HC over lambda. And this is on your formula sheet. This one is not on the formula sheet. So you need to know one thing, what it means to be quantized, like what quantized means. And this means in discrete packets, not continuous. Questions so far, guys? Doing okay? And then the actual photoelectric effect, which is the law of conservation of energy, which says that the energy before is equal to the energy after. And so this is not on your formula sheet. It is as a conservation of energy, which is physics principle number 5. I can never remember 5. Okay. So it says that the energy of the photon is equal to the work function plus the kinetic energy of the electron. So HF equals, I'll just leave work function. Good thing I'm like videotaping this too, isn't it? HF is equal to work plus QV stop. So these, breaking down these this comes from Planck's formula, which is E equals HF. Then the formula for the work function, which is work is equal to HFO. You can also have HC over lambda O. This is on your formula sheet. This is not on formula sheet. And then the stopping potential, which you get from EK max is equal to QV stop. And this is also on your formula sheet. But don't forget that EK max also equals 1/2 mv squared. And 95 to 99% of the time when you're asked to find the velocity of something, you're given the kinetic energy. in some way. It might not just say the kinetic energy of the electron is this, or the kinetic energy of the object is this, but you have to extrapolate from that. If it has energy, its kinetic energy is what it has. And then a little bit of graphing stuff that we did. We looked at two different types of graphs here. Ooh, that's nice. One was energy, EK versus frequency. And the other one is voltage versus frequency, or potential difference versus frequency. In either case, the graph looks the same. Right? It has a y-intercept, an x-intercept, and a slope. So in both cases, the slope equals h. The y-intercept equals the work function. And the x-intercept equals the threshold frequency. For this graph, energy is in electron volts, and usually for this one, energy and the work function is in joules. So this would be energy, work function, and H are in joules. Energy, work function, and H are in electron volts for that. And then the last two formulas on there is just the Compton effect, saying waves have momentum. So momentum is hf over c, or momentum is h over lambda. And then there's this formula to find the change in wavelength if you have a collision, and also know that you can have 2D collision analysis here. And so that's EMR. And then there's a package of questions here. And I just want to point out something about one question that may or may not work the right way. So we may get the right answer, we may not, after we get some protractors, because you have to actually measure the angle. And I don't think increasing the size impacted the angle. Should still say, like, the relative difference between the two angles should still be the same. So that's this question here, this one, this first one here, where you're given this diagram, and the index of refraction of the water is 1.33. You want to know the index of refraction of the second medium. And it says you'll need to make measurements using a ruler or protractor. Protractor will work, right? Because if you get this angle and then you get this angle. So this would be theta 1. This would be theta 2. So then sine theta 1 over sine theta 2 equals n2 over n1. You have n1. You would measure these two angles, and you could use that to solve for n2. Again, the answers are in the back. They're listed in the back. And now you have three packages. You've got your momentum and impulse, you've got your forces and fields, and you've got EMR. Tomorrow we'll do atomic physics, and then the rest of the time, with the exception of probably Thursday, we'll do a little bit of talking and kind of debriefing the field test. And then Tuesday being a rewrite, it's just time for you to work on questions and get help from me.